So with today's lecture, I want to briefly go over kind of a recap of this past week. And then I have some slides on the glass properties and the ion exchange process. Um, so that's kind of what I want to do today. So for the recap, I just kind of wanted to go over, um, what's due this week, what we've done, where all the data is, and things like that. So let's start here in the main share folder. So this is the MSE 407 dash S21. So you should have, this should have been shared with you. So make sure you have that. If you don't have access to this, let me know. I haven't heard anything so far, so I'm going to assume as of now that everybody has access to this. And the first things you'll see are a folder for ion exchange. So this is where all the data is going. We have the first worksheet. Remember, this is a template. And then we have the lab progress form. So let me go ahead and open up the lab progress sheet. So I've tried to organize it by week so that you know what's going on. Week 1 was the design of experiment and those things. So and then you had the pre-lab. So all of that information is still here if you need it. And I also attached the link to the brainstorming document if you need to go back to that. And then week 2, that's what we're on right now. So there was a welcome to MSE Labs video that I linked here that Nancy gave. So this is going to be for a question on the worksheet. So it'll ask you where the available safety equipment is. And so you can find that in the video here that Nancy produced. And then there's instructional videos on the procedure we use to prepare glass, the glass rods, how we sanded the glass. And then since it was kind of long, I split up the ion exchange video into 2 parts. And so you can find the links here. And then the worksheet is linked here if you need it, but it's in the original screen. And again, keep in mind that's due at the end of the week, so Sunday. And then the lecture that we're working on is the link will go right here when we're finished preparing it. And then I already have some videos for next week if you want to go ahead and look at those, but those are over the 4-point bend. So if you want to go ahead and get a head start on that, those are already up. But we'll discuss more as I get the worksheet for those made. Okay, so that's kind of the lab progress sheet. So let's exit out of this. And again, the worksheet's here. So create a copy of it and fill it out as you go through the data and the videos and so forth. So let's kind of go over, where the instructional videos are. If you ever lose track, if I don't have the correct link or something in this lab progress, you can always go to my YouTube page and find it there. I try to put everything in our MSE 407 playlist. All right, so let's look at the data. So this folder here, I have those previous reports from the previous years. I've got this brainstorming document that David prepared for us that we used last week. You'll see this document. This isn't something you necessarily need yourself, but this is something you might see in the videos. And then you're welcome to create your own group information, so you can do that yourself here. And then the other part I want to draw your attention to is the photos. So I've uploaded photos of the process as we've gone through it. So nitrates, we prepared the nitrates for the conditions, and so photos of that are found here. So I have pictures of the nitrates themselves. I've got pictures from when we weighed them out and various things like that. So, and there's also a picture of Nancy's lab notebook here. So that will help you as you try to answer questions about that. Same thing with glass preparation. I put some pictures here. And then the ion exchange, I tried to categorize it by the potassium batches. So the potassium, pure potassium, then those mixed with silver, and then sodium and those mixed with silver. And so there's lots of pictures of the ion exchange process before and after in those cases. And so you can find that information. And then the lab notebook for this section, I try to keep updated here. So there's pictures from our lab notebook that if you want to see some additional details of what we did, those are here. So these are all kind of the resources, the data that you can look at as you're going through and trying to work through the worksheets. So the worksheets are to try to guide your information, but if anything in these folders doesn't make sense, please let us know. We're very open to re-examining something, or maybe we mislabeled something, so feel free to ask us. But other than that, the only other thing I want to sort of draw your attention to as you're going through this process is when you're looking through, the last question on the worksheet, I believe, is to note observations. And so we have put some pictures in here of the glass rods. You can see this is during washing. You can see these are as they dry. So these were just taken out of the ion exchange. So these will help you answer those observational questions. And so we try to get various pictures throughout the process. So pay close attention to those glass rods before and after as they come out to make those observations. And we try to get some more detailed photos throughout this. All right. The last thing I want to mention about the folder structure and so forth in here is that it's very helpful to sort this by the time it's modified. It should pretty much match up with the numbers on the pictures, but sometimes if they get out of order, it can be very difficult to understand the process. So if you sort by when they're modified, that typically allows you to see it in chronological order, so that you can see, this was the first photo I took. So you can see here they're very pristine. So this is before they were exchanged, and then after you can kind of see what they look like. So make sure you kind of look at them in chronological order. That makes the most sense in these cases. So that's really what I wanted to do for the recap. So I'll take a break here, and then we'll come back and look at the slides. All right, so let's go over some basic glass properties to kind of understand the ion exchange process. So on a very basic level, the glasses that we're dealing with are predominantly SiO2. So the crystalline form of SiO2 has long range order. So these are two different crystal structures of SiO2, and they're built around this SiO4 with a 4- charge tetrahedron. So basically the shape, or the silicon with 4 oxygens around it. So it's based around that structure. So there's long range order within this structure. However, our material is a glass, which we know to be amorphous, and so it does still have what we refer to as a network. So everything is bonded, but it's very amorphous in that it has no long range order, right? So this is just kind of illustrating long range order, very repetitive periodic function, and then here a very chaotic random ordering of the same type of network. So it has local ordering in the SiO4 tetrahedron, but beyond that, the long distance order is not there. And this graph is basically just kind of showing that you have a very sharp peak at a low radius. So you have short range order, but there's much more chaotic long range order. If this was long range order, you'd expect very specific peaks in this type of graph. All right, so to make glasses easier to form, we add things called glass modifiers. And basically those modifiers interrupt the crystal formation. So they make it easier to form an amorphous material as opposed to forming a crystal. And so this table from another textbook, which is table 7.7, kind of list the various modifiers and other things as well that we'll talk about. But modifiers are things like lithium, sodium, potassium, cesium, all of these, calcium. So these are all things that modify the structure. So as you can kind of see over here in this visual, basically what they do is they act as free ions. So sodium in this case acts as a free ion, and it's not attached to the network, and as a result it breaks up the network structure. So if it breaks up this network structure, it makes it easier to interrupt crystal formation. And so the more and more modifiers you have, the easier it is to form a glass. And so that has important ramifications for us. So let's look at some compositions. So these are typical compositions that we'll look at, and the amount of modifiers and so forth. So fused silica, also known as fused quartz, is basically just silica. You have very small amounts of impurities, but you also see that the softening temperature is really high, 1600 Celsius. And then if you go down here, we have things like soda glass. So this is more or less soda lime glass. This is very comparable to what we have. And so you can see less silica, but we have more modifiers. So the first one and the most common one is sodium, and that's where you get soda, and then magnesium and calcium. And then you have lead-based glass, window glass, and then electronic glass. But ours is most common, or ours is most similar to the soda silica, soda lime silica, because it predominantly has sodium and calcium. Soda refers to sodium oxide, lime refers to calcium oxide, if you're wondering the naming here. So our glass is often referred to as flint, but flint and soda lime glass are kind of interchangeable. And the other important thing to note here is that you see that the amount of modifiers you add, we're drastically lowering the softening temperature. And so from a industrial standpoint, this is much easier to fabricate these materials because we don't need the extreme high temperatures, right? So that's one of the things we add. So the more modifiers we add breaks up the network and decreases that softening point. All right. Another thing that happens with glass is that the cooling rate, right, that affects the glass properties. And so something that's cooled very fast has a higher volume. Something that has a slower cool has a smaller volume. And it also, if you look over here, these two temperatures, these are in essence the glass transition temperatures. They're labeled differently here, but it can also have an effect on the glass transition temperatures. So the cooling rate in which it happens is affected by that, but also by the composition. This can also affect the glass transition temperature. All right, so let's look at what else happens from increasing the modifiers. So in this case, we're talking increased soda content, so sodium oxide. And so as we increase the soda content, we're going down in the series, and this curve is basically showing the viscosity. So as we increase the soda content, we're actually decreasing viscosity. So that's another one of those things that come about from increasing the modifiers, is that we lower viscosity. So things like soda lime glass are less viscous and therefore easier to work at the same temperature. And again, making it the softening temperature decrease and lowering the viscosity, these all help in sort of workability at the industrial scale or the smaller scale as well. All right, so let's talk briefly about why viscosity is important when we're working with glass parts. So this is a very generic viscosity curve. So this is basically log of viscosity. So again, this is a log plot, so changes in that mean very large changes in the actual viscosity. And then this is temperature. So these are very generic points. So if we go to the highest temperatures here, the viscosity is the lowest. And so this is where we can really easily form or shape or work with that glass. So it's very easy to work. It's much more liquid-like. And so that temperature defined by the viscosity, the lowest, is the working point. And then if we go up a little bit, this range is referred to as the softening point. So this is where it can elongate at about 3% per second. So it's still fairly workable, but it's all defined by the viscosity. And then annealing, this is a point used in glass processing to reduce the internal strain in 15 minutes. So the viscosity is much higher, but we can still relieve internal strain in a rather short time. And then if we go up in viscosity, we see that the internal strain can be reduced, but it now takes 4 hours. So basically, this viscosity curve is kind of showing us the effects it has on workability, but also annealing, because annealing is important. And one of the things I want you to think about for this experiment that we're doing is the interplay between all of these different materials that we're working with. So the nitrates in the ion exchange bath, they only melt at a certain point, and then at a certain point they become unusable, right? So you want to make sure you look at the upper temperature of those nitrates to see what limits us from keep going up and up and up in temperature. And then we have diffusion, right? This ion exchange is kind of an ion-based diffusion experiment. And so we know the general properties of diffusion with temperature, right? But then we also have the glass itself. And so it's important to look at something like this and the properties of the glass itself to understand the effect of temperature that the temperature is having on the glass itself. So I want you to kind of think about all of those various factors, the nitrates, the diffusion process, but also the glass itself. So annealing, when does that happen? Glass transition, all of those factors, when do those happen? And see if you can get a bigger sense of what's happening in this experiment. All right, so let's briefly talk about the ion exchange process that's going to be done to the glass that we have in this lab. So we talked about this briefly in the first week, but basically those modifiers, the network modifiers that we discussed in the previous section, again, they modify the glass, so they're really not connected to the glass network. And so they're more free to move and to exchange via diffusion. So our glass is the predominant modifier is sodium. We do have some calcium as well, but sodium is the big factor. And so before ion exchange, this is what the glass looks like down here. And then we put it into a molten salt bath. And so in this case, it's a nitrate, and it could have potassium. We also have silver, right? So you can see potassium ion is larger than the sodium ion, which takes up this much space in the glass. So the idea of what happens here is that those exchange, right? That's what we've told you. So for every sodium plus charge, we exchange with a potassium plus charge, right? But if this glass structure is fixed in its glassy state, right? So its glassy state means that it's very rigid. So if it's very rigid, then the sodium comes out and it leaves behind this space, and then the potassium goes in, but it's larger, right? So it puts a compressive stress on the area around it to accommodate that size, right? And so that's where we get the compressive strain on the surface of the material from that difference in charge. But it's reliant on the glass being glassy, right, and not accommodating the potassium and rearranging and relieving the strain that occurs from that process. And so this continues to happen the more that it's in the ion exchange bath, right? So you kind of know the relationship between diffusion rates and time, or diffusion and time, but also temperature. Think about how temperature affects the higher temperature, the lower temperature, and what effect that has, and where it diffuses, right? So it starts on the surface, but it gradually works its way into the interior. So it's a diffusion process, but I want to point out that it is charged species, so there is an aspect to this that you have to account for that charge. All right, so the result of this exchange of modifiers for larger ions again creates the compression, and this basically shows it. This is a basically an optical image using some polarizers, so basically a fancy setup to basically show you compression. So essentially, this is the, if you think about this whole uh, thing here as the glass rod, this part on the outside is the exterior of the glass rod, and you see that the kind of the color here shoots up, and so this part, as it kind of creeps into the compression region on both sides of the exterior, is the compressive force that's or compressive strain that's resultant from that exchange. And so you can see kind of the what they call the case depth, so how far it penetrates to the surface. So but the interior is is unaffected, or you can see some tension even on the outside. So, or sorry, very near it. So there tends to be compression on the outside and then tension in the inside to account for that compression. But this is what gives you that strength, because ceramic and brittle materials are stronger in compression. So essentially, if something wants to break this material, it has to counter the compressive strain on the exterior surface before it can break the tension inside. So that's the important part about this ion exchange process and how it works. So again, you want to think diffusion, but also, like I mentioned in the last portion to do with glass properties, think about the interplay between the nitrates, diffusion, and then the glass itself. What about the glass changes with temperature? So all of these things are important when we look at this experiment. And so there's a lot of factors that go into this experiment. All right, so let's go ahead and take a look at bend testing that will be done on the glass rods. So I will give you a separate video on the actual use of the Instron to operate and conduct this test, but here I kind of want to talk about the background of it. So this might look familiar to what you've seen, but this is our test sample, so our glass rod. And then these are the 4 contact points, because we are going to be using 4-point bend. And so you see that the 2 under the inner span, which is the top, and then the outer span is further apart on the bottom. And by moving those closer and closer together, we apply a force, and that is a bending force, because it basically causes the sample to bend downward, to deflect down. So with 4-point bend, this operates and has a maximum bending moment spread over a larger volume than 3-point. So if you're familiar with what 3-point is, basically replace the top 2 with 1 right in the middle. So let's kind of go over what's in these equations, because this is what you're going to be using to calculate the bending strength. So this is the bending strength equation. So it's 16P, and P is the break force. So this is what you'll get from the instrument, from the software. And then A is the bending arm, the moment arm. We'll talk about that in a second. And then on the bottom, since this is a circular cross section, we use the specimen diameter in millimeters. So if we use millimeters for everything and newtons for the break force, this ends up being in megapascals, because that's equivalent to pascals per meter squared. So the moment arm is what they kind of talk about down here. So the moment arm is connected to the spans, the outer span here, which is called L naught, and the Li, which is the inner span. And so the moment arm is the outer minus the inner divided by 2. So if you work that out, if we have a configuration where the inner span is half of the outer span, it simplifies this expression using this formula down here to just be this. So now instead of having to account for the inner span, we only look at the outer span. So our flexural strength is 4p L naught pi d cubed. So we only need the outer span if the inner span is half the length. And so if you look at our configuration, you can verify that that is the case for our setup. But it just makes that calculation slightly easier. So from this, all we need to do is know the dimensions of the glass rod. We need to know the diameter. So the diameter, we need to know the brake force from the software, and then we need to verify the span lengths from the setup. And so with all that information, we can calculate the bond strength or the flexural strength under 4-point bend. So that's the first thing you're going to do with the 4-point data that you receive. All right, so this is just a little bit about that bending moment. So this compares 3-point bend. So again, just 1 point here and then 2 on the bottom, as opposed to 2 points on the top. And so this just shows the bending moment, the maximum. So the maximum bending moment on 3-point is just localized at the top, at the middle, and then it goes down linearly on both sides to the outer contact points. In 4-point, the maximum bending moment is actually spread out along the entire top span, so that whole distance, and then it goes down in this region here and over here. So the maximum moment is actually spread out over a much wider region. And so what I want you to do with that is think about how that would affect the 4-point flexural strength compared to the 3-point flexural strength. Because if you're looking in the literature, you may see 3-point data and we can't directly compare it to 4-point because the setup is different, and this has an effect on the glass itself. So think about that as we're going through this data, and if you're looking in the literature and you're seeing these two, think about which one do you think will be greater than, less than, or equal to, comparing those two values. All right, so I just wanted to give you a brief background into this bending test. Next week, during the week, I will upload some videos going over the process for doing the statistical analysis on this bending data. So we'll go over Weibull data, Weibull analysis, once you have these values of flexural strength calculated. So stay tuned for those videos next week.